So, what do we mean by registration? Effectively, registration gives us the ability to very accurately capture a position. So that if we have got something where, for example, we have a sensor over the material and there's some pattern on it, and we want to actually accurately cut in line with the pattern. Say it's a chocolate bar wrapper or whatever. You don't want to cut halfway through Cadbury's or Kit Kat. You want to cut each package at the end lined up with the printing. So we need a way of very accurately doing that. Doesn't really matter where the input comes from. It could be a proximity sensor or an optical sensor, even an output from a vision sensor, a vision system. So that's kind of a more modern way. You get these cameras over conveyor belts, and they actually pick up various things on there, and with a bit of processing, they tell you where they are on the conveyor. We would need to synchronize that with the controller as well. The kind of line we're looking at, we've got a sensor, very simple one there, just looking at marks on what the material is. Our controllers generally have a special input for the registration. You cannot use any old input because they have some special hardware behind them. So on this particular one, that's an EtherCAT module. There are 8 inputs on there which you can allocate for registration should you want to. On the MC405 that you're running, all 8 of the inputs are dedicated to this as well. They all have the registration hardware behind them. Okay, so you can use any of those 8 inputs on the 405. So imagine our conveyors going along at, say, 5 meters a second. So every millisecond of software ticks. Remember, we update our software every millisecond. So every millisecond, 5 millimeters of material has gone by at that high speed. So we're going to miss it if we look at this external event in software. We're going to be looking at it there, and so we were going to pick up completely the wrong position. This is a bit exaggerated. I mean, if it's not running that fast, you will get some errors. Not as bad as this, but this is obviously quite a major error there. So by using this registration system, we have a command called Regist, and that Regist command will basically cause the system to record that position on the rising edge. It's automatically done inside the hardware. So it's captured into a register, and then we can pick that up later in software with that regpos value. And it doesn't really matter if we're looking at it straight away on the next servo tick, or it doesn't even matter if we pick it up here in the software. If the software only records it 5 or 6 milliseconds later, it's still the correct value because it's been captured in a hardware register. Yeah, so it's very precise. There's the command, Regist with a mode. 20 or 21 is the general command that we use, or the general value we use. You might ask what happened to the others from Regist 0 up to Regist 19. Regists 1, 2, 3 and 4 do exist, and you can use them. They're backward compatible with our older controllers. From 5 to 19 they do exist. They are documented, but they cover all sorts of different scenarios which are all covered anyway with Regist 20. So Regist 20 covers everything. If you were to use Regist 15, for example, if you look at Regist 15, you can do it with Regist 20 because Regist 20 has the ability to basically cover all scenarios. Few parameters there. The channel number is like a logical channel, so that basically saying that you have a 0 or a 1 in there. There's normally 2 channels for each axis, and then the source tells you where it's coming from. So if you decide channel 0 is going to be the first input, then the source would be 0, and if you want the Z, I think it then becomes 1, and the second input it's 2. So the source just tells it where to get the registration input from. You've got rising and falling edge, and you've got the ability to set a window. The window is not really used very often now because most applications there's a dedicated mark for picking up, but the window's there. If you're, say, looking at some material and all you've got is, say, the printing of it might be like the actual printing that appears on a piece of paper or something, or a plastic bag, and you need to actually focus on exactly which part of the printing that you want to pick the registration up on. So you tell it the position where to look start looking and the position where to stop looking for the registration there. So there's Regist 20. You've also got, besides being able to pick up the position, you can pick up the captured speed. This is just actually the software calculated speed, so it's not a hardware capture as such. But if you want to get very precise with getting the registered position, you might want to calculate a slightly different offset depending on the speed. Because even with hardware capture, you've still got a small delay in the sensor and a small delay in our input circuit, so that might have an effect. So you can compensate for that. Mark is simply a flag that shows you that it's happened when the rising edge or falling edge occurs. And then if the channel number is 1, you've just got a B on the end of all of those, so it just gives you the ability to do the second channel. So a little example with boxes on a conveyor. So we just want to zero the axis when the box passes the light beam. So we effectively just use Regist to capture the position. So we need to arm the registration and then use a thing called off-pos to reset the encoder. So this off-pos command, what it does, it basically adds whatever value you've got to the MPOS value. Okay, so it's like def-pos, but it's doing an offset rather than defining it. It's adding that value on. So in the program it's typing in right now. You've only got 3 lines. Regist 20, wait until mark, and then off-pos equals minus regpos. So the way that works is if the box, say the box passes the light beam when the value is 100, MPOS is 100. Okay. Later on, when MPOS, when the box is further down the line, say MPOS is 105, the regpos will be 100. So now we're saying, right, subtract 100 from 105, and it gives a position of 5, which is correct. It's moved 5 millimeters on from the 0 position. So whenever you see in a program off-pos equals minus regpos, it's setting the axis to 0 on the captured position. Yeah, and it does that every time. Now there's another version of Regist which is used for when we're using EtherCAT, because on the EtherCAT system, thing with the Regist is on a real axis like we have here, we're counting the encoder pulses, so we can capture that at any time. But on an EtherCAT system, we only get information from the drive every servo cycle. So every millisecond, the drive updates us with a position. We have no record of what it is in between those two. So one servo period and the next, if that rising edge occurs halfway through a servo cycle, we have no way of actually capturing that. But what we can capture is the time. So with the Regist 21, we capture the time value internally when the registration rising edge happened, and then we can interpolate between 2 points. So we know where the axis position was in one servo cycle, so it might be there, and we know where it is in the next servo cycle. So if our rising edge happened there, we can interpolate that, capture the time, and just do a linear interpolation of position to give us the registration position. And this is what you get when you use the inputs on an MC4N, for example, or an MC664. If you use the 8 inputs on there for registration, it's doing this time interpolated registration.
Oh, the Flex 6 Nano?
Flex 6 Nano doesn't have it.
Doesn't have it?
No. The Flex 6 Nano, you must use the registration that's available on the drive.
On the drive, yeah.
I think I've got a slide about that. Just before I move on, you'll see the syntax of the mark detection is different here. It's R mark and R regpos. And the channel number is simply the input number, so it's quite simple to use. If you put your wire into input 3, you do Regist 21,3, and then you look for R mark 3, and you get R regpos 3. It just all matches, yeah.
But in that case,
well, Regist 21 captures the input of the controller with the time interpolated. If you want to use the drive, we'll talk about that in a second, because the drive will come up, I think. So little example just showing label feeding there. That's using Regist 21, just to show it as an example. But this particular case, it does a move link based on the pitch that's been pre-programmed, and it has a little adjustment in there based on the previous cycle label position. So it's like a feedback loop. So each time it does a move link, it waits until you get the mark or the axis goes to idle. If you do get the mark, it calculates the next error, so it basically takes the reg pos subtracted from wherever the programmed mark position is, because that mark there is not 0, it's somewhere other than 0, so you actually program in where the mark's expected to be, and then it takes about 40% of that and feeds it back into the next move link. And the reason we've got about 40% is it is a feedback loop. It's going back and
to adjust.
To do the next adjustment. If you put 100% back in, it tends to oscillate. It won't stay on the mark. It'll keep jumping backwards and forwards. And we found with experience 40% is a good value. But I have to say, the last time I went to a customer and we were doing this, we found that 30% was actually better on that particular machine. So it does vary a little bit with the machine. Now if it misses a mark, in other words it gets to idle here but there's no mark, it goes down here and there's a little counter and it will just basically go off and sound an alarm if it doesn't detect a mark every cycle. Okay. So that's so just an example, feeding labels onto the previous box that we saw. So on going back to your question about the EtherCAT, if you use EtherCAT slaves which have their own ability to do registration, in the EtherCAT world this is called touch probe, and the registration sensor is actually plugged into the drive itself, and then the EtherCAT master, us, our trio, we can actually arm that triggering system within the drive, and we can get the value back when it has been triggered, and we do all that automatically. And all you have to do is basically set it up in the PDO so it's in the cyclic data, and then just use Regist 20 and it just works. So
just Regist 20.
Yeah, so you go back to Regist 20. Regist 20 does the functionality for touch probe registration in the drive. Yeah. Regist 21 is for using the inputs on the controller with EtherCAT. And Regist 20 again is using the inputs on the controller with traditional encoder axes. Yeah, so there's your touch probe. What ends up with the source kind of depends a little bit on the drive. So you've got to check the drive manual to see whether it may have 1 or 2 inputs. It may or may not allow you to do touch probe on the Z. But you need to check with the drive manual because we are handshaking obviously with the drive. If you use an Eston drive, it has 2 inputs and does the Z, so you have everything.
Yeah.
So, but I know some other drives don't.
Commodore also has the input.
Yeah.
Most of the drives.
Yeah, we have an old Colmorgan drive here and it doesn't have the Z because there is actually no Z on. I think there's no Z on the encoder on the motor. Yes, resolver. Yeah, so there is no Z. Yeah. So. There are a few around that don't have the Z. And there are quite a few around that have only 1 input. Okay, so do you remember yesterday we looked at move modify very briefly? So that can also be used for registration. So we started a move, in this case move apps 100, and then the move modify, when we add it in, we can move up to a different end position. So we can use that alongside registration to say a move stop situation here where we're moving cards underneath a punch. Synchronized with the punch going up and down. So in this case we will start doing the move, and as the little mark passes the sensor, we will then adjust the endpoint of the move to have it finishing in the right place. So a very simple program here. We've got the perfect case what you would have if there was no slippage or no errors on the machine mechanically. We can just simply move the program pitch because it's been very accurately measured and the machine is perfect, and we've just got 3 lines of code. Not the real world, of course. The machine won't be perfect, and even with a laser measurement system, I don't think you could perfectly measure the distance between the marks. So we can add some code onto that, which is another 3 lines doing Regist 20, wait until mark, move modify. So we've got move modify plus an offset, and that's just to allow for the offset between where the sensor's placed compared to the machine. So you have some kind of machine offset there. Well, regpos comes from the Regist.
Okay.
The offset is say really it's just what we're talking about is what's the offset between the center of that and where that sensor is placed.
Okay.
Yeah.
Okay.
So it's just a machine
Installation
dimension,
sensor.
installation offset. Yeah, yeah. And obviously, again in the real world, you would probably have, okay, it's not quite right, so you'd enter something, go up and down on your HMI to adjust that offset to move it into the correct position.
Yeah.
Yeah.
Yeah. Sometimes I try and error.
Yeah, yeah, yeah. There's obviously a problem with that in that if we have wait until mark, if there's a problem with the mark or the sensor, then it's going to get stuck. It won't go past that line. So we need to add even more lines of code to say what if there's no mark. So we're doing, instead of just wait until mark, we're doing wait until mark or idle. And then if we see the mark, we do those 2 lines of code as before, or else we increment a counter and then go off to some routine that will flash a big red light on the machine and stop everything if we're missing too many. So it's kind of, this is a little demonstration of how 3 lines of code that would run the machine develop into like 18 lines of code or something once you put all the what ifs into it. And that tends to be trio programming in a nutshell, really. The motion bit will be actually very small, and we have commands that do it really neatly, and the rest of it will be huge. All the stuff about what happens if someone opens a guard, what happens if an axis goes into error, you've got to add all that stuff in as well.
Hi, this is Reza from Trio US office. In this video, I will show you how to use the registration function by using Trio controller and using the Eastern servo over EtherCAT. So in this way, we have one controller here, which is MC4N, and 2 drives from Eastern. The first one is ED3M, which is a multi-axis and support 2 motors. As you see here, we have screen for each motors like this, and here I can just choose the base 0, for example, which is the first axis, forward this one, and you see here the motor is forwarding, rotating, cancel, and reverse. You see the first axis is rotating in the reverse direction. Okay. So we go to base 1 and forward it. See it's rotating. Cancel, reverse, cancel. So you see both axes are fully controlled by our controller. So in this case, close this page, and you see here I have this very short program for capturing the registration by using a touch probe. Here you see the registration format and waiting for mark, which is if I step the program, you see the program is waiting here in this position and waiting for mark sensor. If we go to user manual of Eastern multi-axis ED3, and we can see there are different digital inputs for axis A and also for axis B, which is the high speed and using for touch probe inputs, and it's different with normal digital inputs. So in this case, actually we already wired both digital inputs for both axes, and if we go to program, here I need to run the second axis, so I type forward running, and the axis is running with the high speed, which is 3000 RPM, as we said here, 50 turn per second, which means 3000 per minute. So in this case, if I activate the digital input, you can see here we have registered position. I already watched the variables, two variables here. I read the M pose of the axis, which is the normal reading axis position, and then the reg pose, which is the captured position by drive and read by EtherCAT. So I proposed these values in these two registers here, two variables, and you can see the difference is very few because I'm just running one program with a high priority. There is no other program is running in this project, and that's why the difference between these two values are too small. The first value is captured position read from the drive, and the second one is the read position from MPOS, which is regularly updating the feedback from the drive. So in this case, you see when I activate it, it captured the new position. So in this case, you can have very precise capturing of position by using the external inputs. You see, this is very straightforward. We're using small program. That's it. Thank you.